problem 1, we have the joint density as 1 plus xy divided by a from x, the absolute value of x less than 1 and absolute value of y less than 1, which can be rewritten as -1 x greater than -1 less than 1 and y greater than -1 less than 1. First, we need to find a so that above density is a joint density function. And then we can simply use the definition and set the bounds of from -1 to 1 and -1 to 1 of 1 plus xy divided by a dx dy equals to 1. And we take a out, which is a constant, 1 over a out is constant, and then we can get that a equals to 4. And then on the second part, we need to find if x, y are correlated or not. In order to do that, we need to find the joint expectation of x and y, which is we take the derivative of take the integral from -1 to 1 and -1 to 1 of xy times 1 plus xy divided by 4, which we replace with for a dx dy. And if you take the integral, we have 1 over 9 as x y. And then we need to find the marginal density, the marginal probability distribution of xy, fx first from -1 to 1 and 1 plus xy over 4 divided by dy, which is only 1 over 2. And fy, from the same method, we have 1 over 2 as well. And in order to find ex, we just take the integral from -1 to 1 of x times 1 over 2 dx, and we should have 0. And similarly for y, we have take the density from take the integral from -1 to 1 of 1 over 2 times y dy, and similarly you have 0 as well. And since that exy minus ex times ey is 0, so we can get to the conclusion that xy are the random variable x and y are in fact uncorrelated, because exy minus exey doesn't equal to 0. And because fy is 1 over 2 and fx is 1 over 2 as well, because exy is 1 over 9 and minus 0 and doesn't equal 0, so this is uncorrelated. And xy are independent because fy times fx, which is a half times a half, is 1/4, which doesn't equal to the original joint distribution that's given, which is 1 plus xy divided by 4. And for the second part, we need to find the joint density of x squared and y squared. And then we just set z equals to x squared and y squared equals to w. And then we find the Jacobian of the joint density. And then we use the formula for xy divided by the Jacobian of fzw, and substitute x and y with substitute x with z and y with omega w. And then after taking the integral, we have 1 over 2 square root of z times 1 over 2 square root of omega. And then we find the probability distribution of fw, which you can use the formula of fw equals to fy of y divided by g omega. And because there are two parts for when omega is greater than 0, less than 1, we have first we take the integral, take the derivative of omega with respect to y. We have y equals to plus minus w, and then we take the integral. We have 2 square root of w. Then we have 1 over 2 square root of w as wy. Similarly, the same step applies for z as well. And because we find that the joint density of fw and fz, we multiply together and we have fzw. So zw are independent, which implies that x squared and y squared are independent.